Hi everyone. So I'm a materials scientist, and people often think of materials and objects as passive and with constant properties. For example, if I'm doing home renovations and I have some boring white wall, what do? I go out, I buy a new paint that I like, and I paint over that wall. But what if instead the wall itself could change its color? What if instead of changing the material, we can change the material's properties? This is exactly what scientists are doing in the field of smart materials. They're trying to create new materials that can change their properties based on an external stimuli. These properties can be anything from something more external and visual like shape and color to more complex properties like magnetic or electronic properties. And the external stimuli can also be anything we can think of like temperature, light, electricity, and so on. So the idea here is to take materials and to turn them from passive to active and enable us to choose the properties of them that we want to use. This also enables a lot of new technologies and applications that are not yet available today. So now we have a lot of materials that fall into this category, and they are used in applications that have drastically changed the way we live. One example here is the light bulb. A light is based on a material that once we apply a voltage to it, it becomes luminescent and emits light. Another example is the transistors, the basis of the chips and computers all around us. They are based on a material that without a voltage, it insulates, and once we apply a voltage, it can conduct electricity, so we can change the electronic behavior of the material. Another example is solar cells that can harvest light energy and turn it to electric energy. So in the presence of light, they create an electric current. Those are all really amazing applications, and now we are trying to create even more smart materials that, for example, can pass between various properties and create very exciting applications. Some of you may have glasses with dimming lenses that can change their darkness as a response to light, or like here at the push of a button, and have various settings of darkness. A similar but very exciting application is smart windows. Smart windows can change their transparency, and that can enable us to control the light and heat transfer into buildings. This is very desirable for skyscrapers, where it can save over 20% of the energy consumption on cooling and heating. Those are two examples for application that can be created with a type of materials called electrochromic materials. Those are materials that change their optical properties like color or transparency as a response to voltage. So we all know the regular displays that we have in our computers and phones and tablets like here. And they are based on light emission. Each pixel can emit a light, and we can control the color that it emits. But some of you may also have an electronic book that is based on an electronic ink display like we see here. This is a special display because it's not based on light emission. Each pixel can change its color between black and white. This is very good for a few reasons. One is that blue light emission can damage our eyesight, and this doesn't emit light, so it's very good for the eyes. And another that it has very low energy consumption. So the only energy we need in such a display is to change the pixels from black and white. But if the picture sits still, it doesn't consume any energy at all. That's why some of you with such an electronic book know that it can go even over a month without charging. But already here in this picture, we can see the main disadvantage of such a display. It's black and white. If we could get a full color display, then we could we could use it in our daily life a lot more. And the reason that we can't do it is that we don't yet have good enough electrochromic materials to reach a very wide range of colors and have a full color display. And now I want to talk about one of the main challenges in the field of electrochromics and smart materials in general, and that is tunability. We want our materials to be able to reach a very wide range of properties and to pass between them easily. That way we can finely tune them to be compatible with many new applications. This is what we are trying to do in my lab, to create new electrochromic materials that can be very finely tuned and compatible and create many new applications. Here is an example of something that we can create in our lab. This is an electrochromic coating on top of glass. And now you can see how it passes between purple and transparent once we apply a voltage. We have many coatings like it in many different colors, like orange, gray, and more that I don't show here. And they're all based on a type of material called a metal organic complex, which is made from a metal ion that is bound to organic molecules. The color of this complex comes from this connection. And that's why I can get many different colors by choosing different metal ions and organic molecules. Then once I apply an electric voltage, I take an electron from this metal ion and change its charge from 2+ to 3+, which also changes the color of my material. So this is my electrochromic material, but I still need to find a way to create a coating from it. So the first thing I need is a compatible surface. I want it to be transparent so I can see just the color of my material, and I want it to be conductive so I can apply a voltage. Then I apply a linker to it. The linker can attach both to the surface and to my complexes. Then once I apply the complexes, they attach to the linker and I get a coating. I can repeat this process many times to get a thicker coating with more intense colors. And this sort of method is called a layer-by-layer assembly, meaning that each layer is created separately from the other. So in each layer, I can choose which metal complex to use. I can choose how many times, how thick do I want this layer to be. And this gives me a lot of freedom to choose how my coating will look like and to tune its optical properties, electronic properties, thickness. And here you can see many of the films that we can create in our lab. And you can see that we have a very wide range of colors and intensities that are based on which complexes do I choose and how many times do I apply them. Another great thing that this method allows us to do is to create more complicated devices that are based on different layers. Here is an example for a memory device that is made from 3 layers that differ by their metal ion. So the first layer is ruthenium, then iron, then osmium, all just the names of the metal ion that we chose to use. Those complexes are different by their color and by the voltage in which they lose an electron. So we managed to create 4 different states for this same coating that occur in different voltages. Each of these states has its own unique color, its own unique optical signature. Since once a complex loses its electron, it also changes the color. This is very similar to a memory component in our computer. This component can create a charge as a response to voltage, and that's how our computer stores data. But in a computer, right now, there are only 2 states. It either has charge or it doesn't. But we have a 4-state memory component, which is very unique because that way you can store more data in the same amount of storage. Another really cool thing that we can do with this is to integrate it with a conventional circuit board that can read out a unique electric signature for each of these states, and in turn, a bulb lights up that is unique for each state. This is really amazing because our materials are not the materials that people usually use in conventional technology, but still we were able to implement it into a conventional circuit board and make it work like a memory component. So here I have showed you how we can take our materials and through this method of layer-by-layer assembly, finely tune them and make tailor-made applications. So we can create with this material smart windows that we saw. We can work on electrochromic displays thanks to the wide range of colors that we can achieve. and we can even create electronic components like the memory device we just saw and many others that we are working very hard to achieve in our lab. And I hope that I also showed you the great potential that smart materials have on technology and how we can create new and tunable smart materials. And I believe that in the coming years we will see more and more smart materials in our daily life. I want to thank my group and my advisors, and thank you, and the organizers of the conference, and thank you for listening.